Alright, so I'd like to take a look at the 2-9 notes today. And in 2-9 what we're going to do is we're going to say, alright, we've looked at direct variation, we've looked at inverse variation. What happens if we have more than one independent variable? And how can we look at if there's multiple types of variation that's going on? And there's two terms that we're going to look at today that revolve around that concept. The first is combined variation. And in combined variation, what we have is we have a situation where we have both direct variation, okay, both direct variation and inverse variation. So, sorry, I'm trying to get my pen here. So we have direct variation and we have inverse variation. So here's an example of an equation that involves both, and we can say that S varies directly as R and F and inversely as B. So that's how we would read something like that. So we have three independent variables there, R, F, and B, and then we have one dependent variable, and that's S. So the dependent variable has a relationship directly with R and inversely with, directly with R and F and inversely with B. All right, this example will deal with the equation that we have up above involving combined variation, where S is equal to the speed, R is the number of revolutions per minute, F is the number of teeth on the front gear, and B is the number of teeth on the back gear. So those are kind of our variables that we're working with. And K obviously is our constant of variation. It says a bicycle is pedaling at 85 revolutions per minute using a front gear with 39 teeth and a back gear with 13 teeth. At these settings, she is traveling 21 miles per hour. Describe how her speed would change if she decreased her pedaling to 60 revolutions per minute. Okay, well, in order for us to do that, we're going to first need to figure out what K is based on the information that we're given there. And we know that we know what the speed is. We know that that's 21. We don't know what K is, but we know that the revolutions is 85. And we know that the number of teeth on the front is 39. And the number of teeth on the back is 13. Okay. Now there's a couple ways that I could do this. I can just multiply both sides by 13 and divide both sides by 85 times 39. Or I can just get a value for 85 times 39 divided by 13, which then I can multiply by K. And I'm going to go ahead and do that part first. So I'm going to take my calculator out and I'm going to take these two values here, multiply them together and divide by 13. So if I do that, I get 255. So I would say 21 is equal to 255 times K. And then I can divide both sides by 255. And I can get my value for K. So if I take 21 divided by 255, that gives me about 0.082. Okay, so now that we've found K, we're going to plug that back in to our original equation here. So I'm going to say S, which we have right up here. So I'm going to say S is equal to 0.082 times RF divided by B. Now I want to find that speed when the revolutions is changed to 60. Okay, so we're biking on the same bike, but now I'm going to change my revolutions to 60 as opposed to the current revolutions, which is 85. Alright, so let's plug that information in to get our speed. So speed would be equal to 0.082 times the revolutions, which is now 60, times everything else stays the same, so the front teeth would be 39 and the back teeth would be 13. Now I'm going to go ahead and use my calculator to come up with that value then. And if I do that, I would get a speed of 15 miles per hour. So by decreasing our revolutions from 85 down to 60, okay, our speed is going to go down to 15 miles per hour. All right, so the second term that we have in this section is the term joint variation. And joint variation is a situation in which one quantity varies directly as the product of two or more independent variables. So basically we have a dependent variable that varies directly with at least two independent variables, and in this situation there is no inverse variation that goes along with it. So this example of y equals kxz, so x and z are independent variables, y is dependent, and we could say that y varies jointly as x and z, or we could say y varies directly as the product of x and z. So let's take a look at this guided example. It says the volume of a solid with a circular base varies jointly as the height of the solid and the square of the radius of the base. And these are kind of the things that we want to do. So the first thing we want to look at is writing a general equation to model this situation. So generally it says as circular base, volume of solid with a circular base varies jointly. Well, which ones does it vary with? Height and the square of the radius. So if I'm going to write a general variation equation for that, here's how I'm going to write that. Volume equals K times H times R squared. Okay. Part B says if the volume of the solid is 47.1 cubic inches, when the radius is 3 inches and the height is 5 inches, find K. So now we're going to go through that process of finding K. So I'm going to plug in the 47.1 for the volume. I'm going to plug in my two values for height and radius, and I'm going to solve for K. And you'll notice if I do that, I get a K value of this right here. Okay. Part C says the value of 3K is approximately equal to what famous mathematical value? How can you express K in terms of that value? So if I look at 3 times K, well, if K is 1.046, if I multiply that by 3, I would get about 3.14, which we know is approximately pi. So we can say that K can be expressed as 1/3 of pi. If 3 times K is equal to pi, then pi divided by 3 would be the same as K. So this is how we could express that. Okay, and then finally, part D says write a variation equation for the situation using the answer from part C. And you'll notice that that is the volume is equal to 1/3 pi r squared times h. Of course, I left h off there originally, so it'd be 1/3 pi r squared h. And then it says that part E just says what well-known solid figure could this be? That would be the volume of a cylinder, because a cylinder would have a base that is a circle, and we would multiply the area of that circle times the height of the cylinder.